In this episode, I will be discussing about the type of microscope. Basically, there are two types of electron microscope. One is called scanning electron microscope and there is called transmission electron microscope. In between these two also, there are other microscope like reflective electron microscope and low voltage electron microscope. Those are not very much popular and not of very extensive use, but they also will be discussed little bit. In this scanning electron microscope and the transmission electron microscope, there are lenses, similarly like optical microscope, but the lenses are electromagnetic and electrostatic. So this depending upon the structure and type of reflection we want, the type of divergence, the type of convergence, all those things is done using electron optics, and this will be discussed in this series. To understand this, we must know what is the type right from the beginning, the top of the microscope. It is, if you look at it, it starts with the filament. What is the type of filament we use? There are three types of filament. One is tungsten filament, another is crystal like LaB6, lanthanum hexaboride. Other one is FEG, that is field emission gun filament. These three types of filament, the basic difference is that they are very commercially, they are very cheap. Right from the first one, the tungsten, the next costliest is the LaB6, then the FEG gun. Apart from that, the most important part is illumination. Right? If you take an illumination unit of 100 in tungsten, it will be 1000 in LaB6, and if you go to the FEG gun, it is 10,000. So this illumination, you understand by common sense that if the room is not lit properly, you cannot see things properly. It is exactly like that. If you put a bright light, you can see a very beautiful things what is available in this room. Even if the light is very less, many things you will not be able to see and appreciate. So it's very important that we go for the high illumination, but the cost matters and the complicacy matters. To do that, we require the FEG gun is very costly, and also we require high vacuum, always maintenance. We cannot put them off around the time it has to be standby. So those complications will be there. Next comes the lenses, the electromagnetic lenses. In the electromagnetic lenses, as you see, the electron beam is generally obeys the laws of physics. That is electron beam. It is called Fleming's left-hand rule. That is electric field, magnetic field, and the field of direction. These three work together. If electron beam is coming in this direction, if you have a magnetic field, an electric field, this keeps on changing its path. So that changing of path is being used. The concept has been used first. Basically, the understanding has been used by Knoll and by Ruska to understand that how electrons can be bent and we can magnify. The next part is the lens system. There are two types of lens system. One is called objective and this is called condenser. The objective is the below region of the near this thing. The top region where the electrons start is the condensing lenses. So these condensing lenses and objective lenses are mainly to converge and diverge the electron beam. Most important is how to observe them. So there is a plate basically for the electron beam to fall, and sometimes it is coated with fluorescent like zinc sulfide. For the electrons, once it falls, it will get an image, otherwise you cannot see the image. So that is called the camera. You can convert that to a computer to see the images. So this complete system is called actually microscope. The two most important thing you must remember while you try to image is the magnification and resolution. You can magnify by lenses, but whether resolution remains or not. How to understand resolution by common sense? If you just take a small hand lens, as you know, and you could try to draw two very small dots using the lens, and then remove the lens, you will be able to see one dot. As explained, the two distinguished objects very fine. If they are not able to see, then it is called not resolved. Why? So magnification as well as resolution both has to be brought together to get the real image. So with this understanding, what we try to understand now, that in the whole system we know that how things were improved subsequently. I like to emphasize now that what happens when an electron beam converges and then it falls on your sample. After it falls on your sample, it is called interaction. Electron interacting with matter. This interaction, after happening, what happens? Some of the electrons will bounce back, some of the electrons will go inside, some of them will be absorbed, and after interaction, there are two types of interaction possible. One is elastic scattering and that is inelastic scattering. These signals were reflected back from the surface, then it is called scanning electron microscope. If it is transmitted through the sample and we collect the information at the back focal plane, it is called transmission electron microscope. If it is inelastically scattered by the outermost electron, incoming electron get reflected from the outermost electron inelastically, then it is called a secondary electron. If it goes inside and with high energy, it goes towards the nucleus and it gets elastically scattered, we call it backscattered electrons. These two is very important once you want to do scanning electron microscopy. The first electron, which is called secondary electron, which is reflected, gives you surface information and gives you very good depth information, so you get secondary electron image. The second one is called backscattered information, which goes towards the nucleus, and you must be remembering in your school days where the nucleus is consists of electron and proton that reflects the electron, so it tells about what type of material it is. That means you can find out what is that material. Suppose you have two different combinations, a aluminum and a titanium, you will get two different contrast, so that is called backscattered image. So these two type of images are very essential to characterize the surface of any material. The basic difference between a scanning electron microscopy and transmission electron microscopy is that apart from that one is reflected, another is transmitted, the basic difference is that there is a scanning coil in scanning electron microscope. That is, it does rastering. I just give example that in this room you have only a torch and you try to see what is there in the room. So what do? You start focusing a torch from one corner, it goes to another corner, then come one step, and then again you scan it back. So this is called rastering. That means you go one step full, take one step in horizontal directions, takes it back one again horizontal direction. So this horizontal, vertical, horizontal, vertical, horizontal, vertical makes it a raster scan. This raster scan, that's why it is called scanning electron microscopy. It scans the surface. This gives a full image of the surface. Basically, it's very important to do fracture analysis. Any material fails. Like if you do a pin, if you take a pin and keep doing like this, bending, it fails. How to understand how it has failed? If you study how it has failed, it is called fracture studies. That is very important in scanning electron microscope. Whereas in transmission electron microscope, there is no scanning coils. The electron passes through the sample. So the important part is that the sample has to be absolutely thin, almost towards zero thickness. That means electron beam should pass through that. Is the true thing. Apart from that, the basic difference is that in scanning electron microscope we use 20 to 30 kilovolt to generate electrons, whereas in transmission electron microscope 200 to 300 kilovolt we use to generate electron. You understand one word. So the complicacy and the system and the cost keep on increasing like that, as well as the operation. In scanning electron microscope we can resolve maximum up to 1 nanometer, whereas in transmission electron microscope we can resolve up to 0.01 nanometer. This is the resolution we can start getting. Now we are approaching actually less than Armstrong. We are approaching 0.75 Armstrong resolution in a high resolution transmission electron microscopy. In the subsequent episode, I will be discussing what are the different types of microscope, how details you can know about it, what are the type, how to use it. All this will be discussed in the subsequent each chapters or in each episodes.